Okay. Ah, yes, thank you. So basic assumptions in framing and LPP. So what are the basic assumptions in framing and LPP? See, once you have the word assumptions, no, the minute you hear this word, it means that the model is not an accurate model. It will work only to a certain extent. Whatever you model, okay, apart from being a mathematician, as a general person, I tell you, maths cannot be used for modeling real time problems. Simulation is the best in real time data, okay. So, like you have lot of things like sim events, you have lot of toolboxes in MATLAB, all those things will give you more accurate results. But this was found nearly about 1 century before during World War II. They found this out, this technique for optimization. Now we also have softwares running on this technique and they give you more accuracy by considering even your variables not to be integers but as fuzzy numbers. Okay, that development is also there. So now anyway, coming to our topic, we have to talk about the basic assumptions in framing and LPP. So what are all the assumptions? The first one is proportionality. So the contribution of each variable in the objective function or its usage of resources is directly proportional to the value of the variable. So the value of the variable is directly proportional to the contribution that it gives to the objective function. That is the first one. Next is additivity. So what do you mean by additivity? The sum of the resources used by the different activities must be equal to the total quantity of the resources used by each activity for all the resources individually or collectively. Simply speaking, additivity means what? You have some resource. How much you use, if you add all that usage, it should be equal to the total available quantity. For example, say, let me say I am going to have 100 bags of rice. Okay, so 60 of you are there for me. I start giving away each one of you one bag, one bag, one bag. All of you start cooking and eating. At the end of 1 month, say maybe some of you have consumed more, some of you have consumed less. I have around another 50 students who have consumed more, and so the bags are empty. So I want to replenish it. That means I want to fill the bag again. Suppose I want to fill the bag again, what should I do? I should open my the remaining sacks, and once again I will fill for everybody. So when can this be done? Only if I have the resource can I ever share the resource. So what happens? The total amount of rice that you consume should be equal to the amount of rice that I have, isn't it? Whether I take register number 1 to 63 plus that 108 and add individual, oh, you ate 800 grams, he ate 1 kg, he ate 15 kg. Like that, if I add, I'm getting 100 kg. And I have 100 kg of rice. It should tally. If it has to tally. You cannot eat 110 kgs of rice from me when I have only 100 kg. Only if I have, you can use. Only if the resource is available, you can utilize. And the sum of the resources that we use for different activities should accumulate together to be equal to the total quantity of resource that is available. That is what is meant by additivity. Next, divisibility. The variables are not restricted to integer values. You know that for sure. In the previous problem, we had x1 by 60, x2 by 75 and all that. They need not be integers because x1 and x2 need not be divisible by 60 or 75. Then, certainty or deterministic. What we did, from the beginning, we kept the coefficients of the objective function and constraints as fixed. Come to this problem, we were talking about the entire problem keeping this 8 ounce. This is our coefficient 8 ounce and 16 ounce. Did I say starting I made 8 ounce, 16 ounce, then I made 7.5 ounce, 15 ounce? No, not like that. What you start with, you fix with the same thing till the end. Okay. Then, that's what is known as certainty. Coefficients in the objective function and the constraints are known. They don't change during the period of study. Next is finiteness. I have infinite number of variables. No, I have always been dealing with finite number. Maybe it can run for 100 different types of bottles with 100 capacity, different capacities. But now I cannot say infinite bottles with infinite capacity, not feasible. So finiteness is important. If we go for that farmer problem, what we did, we considered only three vegetables. I cannot say infinite variety, only finite variety of vegetables. We considered lettuce, radish, and what else? One more we considered. No. So like that. Next. Optimality. So what is our main idea? We want to frame an LPP to optimize the solution. Why do you use this word optimization? If it's a profit, it should be maximization. And if it is going to talk about loss, that means how much you are going to give, then you should go in for a minimization. So in general, we use the word optimization and hence optimality. So these six basic assumptions are required to deal with any LPP problem. Okay, so for dealing with any LPP problem, you should know all these six restrictions. Keeping this in mind only, we develop the problem. Now, what I'm going to do is, I'm not going to give you the method for graphical solution. We will take a small sum and using the problem itself, I will illustrate the method. Okay, then we can have the theory portion. Maybe I will type and even post it in your GCR. Otherwise, everybody will sleep after lunch, including me. Right. Other than this, what more you need to know? One more thing what you need to know before stepping into graphical method is what is a region. These definitions are important. So your first definition, region. What is a region? So take down a region or set of points, that too, not just a region, we are much more bothered about convex region. This is very much important. A set of points is said to be convex. A set of points is said to be convex if the line joining any two points, a set of points is said to be convex if the line joining any two points if the line joining any two points lies completely within the region. Any two points lies completely within the region. We'll give a small example. Completely within the region. So let us take a very simple example, maybe a circle or a sphere, that is a simple closed curve. So this is a simple closed curve. I'm considering a circle. Let me take 3 points. So I want to join these 3 points. This is 1 point and this is 1 point. It lies entirely inside this. Therefore, the region is convex. Suppose I have like this. Suppose I have a region like this. I have points. I have everywhere I have points in this region. So suppose I join these 2 points, they lie inside. But however, if I want to join these 2 points, they lie outside this region R. Therefore, it is not convex. So if you take any 2 points in this region and you want to join them using a line, say you have these are the points that I have considered. The line joining these 2 points should lie within the region. If it lies entirely within the region, for example, I am taking any point here. Look, here it lies entirely within the region, therefore it is convex. Here it doesn't lie within the region, therefore it is not convex. Say some other example we want to have also, we can have. Say suppose I am going to have a region like this. Now look at this. Here also it goes outside. Here also it goes outside. But however, these 2 points lie within the region. But when you connect these two here and here, it goes outside the region. Therefore, this is also not convex. This is also not convex. Only that is convex. Any problem for anybody? You're able to understand what is convex and what is not convex? Suppose you have an angular region. Say you have an angular region. Angular means what? It's like a donut. point, therefore it is not convex. Yes. Any other region? Any simple closed curve alone, if you take, it will be a convex region. See, here I take a point, here I take a point, I can go within, therefore it is convex. Suppose I take a point in this edge, I take a point in that edge, I need to go out, therefore this is also not convex. Your square is convex, your rhombus is convex. Any point you take, you can join, it will all lie inside. So this is a convex one. Now clear about the idea of convexity? Okay. Now we do a small problem. We'll try to solve the problem using graphical method. As I go about the problem, I will give you the steps. Okay, I am not dictating it as theory. Right. So take on. Solve the following LPP. Solve the following LPP by using graphical method. Solve the following LPP using graphical method. So you should use a graph paper to do this. Now for classwork it's alright, but otherwise you have to use a graph paper and you have to plot it in the graph. So you can maximize Z equal to 3x1 plus 2x2 subject to minus 2x1 plus our x2 is less than equal to 1, our x1 is less than equal to 2, and x1 plus x2 less than equal to 3, and x1 comma x2 are greater than equal to. Now, what is the first thing that we are going to do is we want to represent this in a plane. That is, using a graph, you have an x-axis, you have a y-axis, so we are going to represent it on a plane. Step 1. Write inequalities as equalities. This is the basic step. Write the inequalities as equalities. Number 1. Number 2. Draw the lines. Number 3. Mark the region. Okay, this is for layman understanding. If you look into any book, they will not give like this, they may give it in a different manner. Then mark the region. This much we will do by the time will be over. Then I will tell you what is meant by feasibility, how do you go about it, what is a corner point, how to get the convex region, all that we will see. Okay, so now what I have to do? Minus 2x1 plus x2 equal to 1. So I will go for minus 2x1 plus x2 equal to 1. I have to write the inequality as equality. Put x2 equal to 0. Then what happens to my x1? x1 is minus half. Put x1 equal to 0. What happens to my x2? x2 equal to 1. Now what you do is you take this and you try to plot this on a graph. This is x-axis and this is our y-axis. So we can run up to 2, we can run up to 3. So this is going to be my origin 1, 2 and 3. Similarly, here I will have a 1, I will have 2, I will have 3. So if I come down, I may have a 1, I may have a 2 if it is necessary. We will also have this region over here. You will have a minus 1, you will have a minus 2. So typically in graph, I want to draw this line. I have my x-axis to be called as x1 and my y-axis is nothing but my x2. So when x2 is 0, x1 is minus half. This is the point. What point is this? This is minus half comma 0. Then x1 is 0, x2 is 1. So x1 is 0, x2 is 1. So I have my line running like this. So this point I will take as, what is this point? 0 comma 1. So this is 0 comma 1. This is minus half comma 0. So this is my line 2x1 plus x2, 2x1 plus x2 equal to 1. Okay. Then I will come for the next. What I mean? I have to go for the second constraint. What is the second constraint? I have x1 less than equal to 2. So I will take x1 equal to 2. So x1 has to be 2. It's going to be a line which is going to run parallel to your y-axis, and this is going to be my x1 equal to 2. So this is going to come and cut somewhere over here. Now look at this point of intersection. In this line, x1 is 2. So minus 4 plus x2 equal to 1, or x2 is 5. So this point of intersection will be 2 comma 5. So this is my line L2 and this is my line, let me call it as L1. Okay, just observe here. I will redo the problem and I will explain the whole concept once again. We are just plotting it, that's all. Now come here. What else I have? x1 plus x2 is equal to 3. My last constraint, x1 plus x2 value equal to 3. So the points of intersection is, if x1 is 3, x2 is 0, x2 is 3, x1 is 0. So I have to run from 0, 3 to 3, 0. So this would be the point. Okay, so I will change. So from 3, I have to come here. I will take this point as 3. So this point is the point 3 comma 0, and this is going to be the point 0 comma 3. So this is one point and this is the other point. Now look at this. This is our line L3. Now how to trace the region? Everywhere it is telling less than equal to, less than equal to. So since it is telling less than equal to, less than equal to, now look at this. For this L1, less than equal to L1 will be this region which I am shading in yellow color. Okay, less than equal to L1 means this portion, entire portion. Here also it will be there. All this portion which is less than L1. Then what else I have? The portion which is less than equal to x2 equal to 2. Now what is this? x1 is less than equal to 2. So x1 color we are choosing it to be some blue color. So x1 is less than equal to 2 means it will run infinitely and it will come here. It will run infinitely. It will come here, 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 everywhere. This is x1 less than or equal to 2. Now look at this. This entire stretch is involved. Then x1 plus x2 less than equal to 3. Maybe we can use a pink color. So x1 plus x2 less than equal to 3 will be which portion? It will be this portion where it is less than or equal to 3. It is going to be this portion where it is going to be less than or equal to 3. Now what is our feasible region? In our feasible region, all the colors should be involved. See, less than equal to means here also it will run. But what is my feasible region? In my feasible region, all the constraints should get satisfied. So where all three colors are available. So all the three colors are available only in this particular region. Isn't it? Yellow is there, blue is there, everything is there. So this is my feasible region. So let us name the feasible region we have O, we have A, we have B, we have C, and do we have any other line? Yes, we have C. So OABCD is our feasible region. You're able to understand how to mark the region? That's all is needed. Okay. See, you draw the lines first. What you will do? Make the inequality as equality. Draw the lines. See the region which is common to all the lines. Shade that region. If you look at this region, this is a convex region. The points that you have here, that is O, A, B, C, D, they are known as corner points. Your O, A, B, C, D are known as your corner points. So based on this corner points, and we have to find what is the value of these four corner points. Once we come to know the value, we will substitute the value of each point in our objective function. Whichever value gives the maximum for the objective function, that particular point is our answer. So that will give number of x1 and number of x2. Okay. Your time stops here. You have to go for next class. So we'll continue in the next class. From the figure, I will start. Okay.